Yes, thank you, Tina. So now I will start with my presentation. So today I will be talking about nanocellulose in barrier packaging. So I will briefly give overview of what barrier packaging is and what is being done. And then I will talk about a part of my research where we have used nanocellulose as a coating layer for barrier applications. Yes, so I want to start by showing what barrier packaging is made of. So for example, if you take a carton box, for example, like a milk carton or a juice box, and then if you open it up and then try to separate all the layers, we see that it is most often a multi-layer structure. On the first look, it looks like, yeah, it's made out of paperboard, but like you see here, the paper is just there for stability and strength. But then it has many different layers, mostly 4 to 5 layers at least, and each layer provides different functions. So if you want a liquid barrier or moisture barrier, so they usually have a very thin layer of polyethylene coated on it, and aluminum foil can also be there if we need oxygen barrier or some other form of gas barrier, such as aroma or something. If we pack like say coffee or chocolates or something like that. And then there are many other products where we have different barriers, with different materials that are coated to give different barrier properties. But then most often these barrier coatings, they are all plastics, polyethylene, polypropylene, and things like that. And if you look at the global plastic production since 1950s, that's when actually we started using plastics on a large scale. You can see like a majority of them are single-use plastics, and their fate is so after we use them, they either are discarded into landfills or incinerated, but the majority of it is discarded. And if you see the green one, it's very small percentage that is actually recycled, and they are also like maybe recycled once, and then eventually they end up in the same stream, which is either discarded or incinerated. And then if you look at the total percentage of plastics ever produced, we over 40% of them are actually used for packaging. And here I have data about plastic production, and then how much of that is ended up as waste, say from 2015 in different sectors. And like I said, packaging takes up a very big share of the total plastics produced, and almost all of it is thrown away as waste immediately after use. And then if you look at the recycling rates, EU is doing quite good with 42%, but around the world it is very, very small, which is less than 10%. And then all of this thrown away packaging gets ended up in the landfills, which will eventually get accumulated into our water streams. And then also we have this municipal solid waste, which is basically the packaging waste that we get from. So we are, as the population increases, we start accumulating more and more waste, and it is set to cross about 2 billion tons in the next 4 years, and even more if we do not have good alternatives where the packaging biodegrades. So that is one reason why we have been trying to use more biodegradable materials, and nanocellulose is one of those potential candidates which can be used as an alternative to plastics in packaging. So I want to start with by showing this figure on the right. So there are two important barrier properties to consider when we use a material for packaging. One is the oxygen barrier, and then the other is the water vapor barrier. So we have different materials. So lower value is higher barrier. So lower oxygen permeance and lower water vapor permeance. So if you see, very common ones are LDPE, low density polyethylene here. So they have very good water vapor permeance, and notice that the scale is logarithmic. So even a small shift is actually a very big change. So we have the polyethylenes, low density and high density polyethylenes, very good water vapor permeance, but they do not have good oxygen barriers. So most often they are added with aluminum coating on top. Then we have PETs, which are okay. Then metallized plastics are the best ones, which have both oxygen and water vapor barriers. Nanocellulose has been uh, gaining interest mainly because of its very good barrier against oxygen, and then it also has good barrier against grease and mineral oils. So if you talk about two types of nanocelluloses that I have used a lot in my research, one is microfibrillated cellulose. So it's just mechanically fibrillated into smaller dimensions. So with diameters about 20 to 60 nanometers and a few micrometers in length. I will call it as M just to shorten it. And then another one, which is carboxymethylated cellulose nanofibrils, so which has a chemical pretreatment and then mechanically defibrillated. So they are much more finer with diameters less than 15 nanometers and even shorter length scales. So if you make films out of them and then if you measure the oxygen barrier, they have very good oxygen barrier, almost one of the best in the whole list. But then the water barrier is not very good. So the aim has always been that if nanocellulose has to be used as a barrier packaging material, that it needs to be as close to the red box as possible. So there's a lot of research that is being going on, and one of the major challenges that these materials face is that they have very high viscosity and yield stress. So if you want to use it in a road to roll process, these start to create issues with pumping and with getting a good coating quality, applying them as a thin layer on a substrate, etc. And then of course they have the cellulosic materials do not have moisture barrier, so they are very bad at it. So these two are the major challenges that need to be solved if we want to use nanocellulose as a barrier material in packaging. So if you look at the rheology, they have an interesting property. So here I have for these two same materials, the MFC and CNF, now both around 2 to 2.5 weight% suspensions. They are highly shear thinning. So the viscosity, as you increase the shear rate, it falls by almost 4 to 5 orders of magnitude and almost approaches to that of water. So here I have like a picture of a 3% MFC. But then when we pass it through a narrow slot die, I have a cross section here, which is a very small gap. And if it is pressed to that, so you have very high shear rates, which go to the square of this is the shear rate. So it goes to the square of the gap, inversely to the square of the gap. So the smaller the gap, the larger the shear rates we get. And you can see now the suspension, which is almost gel-like, starts almost flowing, forming a nice curtain there and flowing almost like water. So we can use this geometry as a coating head to apply nanocellulose as a thin layer onto paperboards. So slot die coating of nanocellulose. So this has been a very important aspect of my research. In my PhD, so we take the slot die and then we have a pressure vessel and a gear pump that supplies the suspension, and then we apply it on a moving paper web. There's an image here, and then we have a bunch of dryers to dry it, and then so this is a roll-to-roll process. The pilot coater that we have at Akademi, we can run up to 50 meters per minute maximum line speed, and then we can get about 300 millimeters wide web, but the slot head that we made can coat up to 100 millimeters at the moment. And the speed then is also dependent on how much water we have to dry. So like if we use a 2 to 3% nanocellulose, then we are restricted by the drying capacity. So we usually run it at around 5 meters per minute here. So in some examples, we started with the pigment coated paperboard as a base substrate, and then did two different coatings, one with MFC and then one with CNF, and both of them have carboxymethylated cellulose as a rheology modifier. So MFC we were able to get about 12 grams per square meter grammage, and then CNF a slightly lower, mainly because it has low solids content. Yes. So the first problem with high viscosity can be tackled with using a slot die, but then the second issue is with the moisture protection. So one solution is to have a multi-layer structure with a moisture barrier coating on top of nanocellulose. So, and then also we wanted to have a biodegradable structure. So whatever we apply on the top must be biodegradable. So one method is to have an extrusion coating of thermoplastics. LDPE is can be used as a reference, but then there are other polymers such as PLAs, PHA, PBAT, and PBS, which are biodegradable. So they can be applied on top to protect nanocellulose from moisture. On the other hand, there are these so-called water-based dispersions, which are based on, again, the same polymers, PLA, PHAs, and then we have mineral pigments and bio-based latex-based dispersions, which can be applied as well. They give the same kind of protection. So the whole concept is to have similar to what I showed in the first slide, like a multi-layer structure where paperboard works as a support, and then you have nanocellulose for oxygen, oil, and grease barrier, and then a water vapor barrier on top. So in the next slides, I will just talk about extrusion coating. Just as an example, we've been doing water-based dispersion coating as well, but I think we don't have enough time to go through all the details. So I will just talk about extrusion coating thermoplastics. And then we've been looking at different role played by different nanocellulose types, like if it is mechanically defibrillated or if it has some chemical pretreatment, how the polymer on top, the extrusion polymer influences the barrier properties. And then if we add some pigments into nanocellulose, would that affect barrier, or and then how the adhesion between the polymer and nanocellulose would be, and then also how plasticizers affect the barrier properties as well. Yeah, so when it comes to thermoplastics, over 90% of the mass of plastics produced in the world are thermoplastics. So they can be processed via many methods such as injection molding, blow molding, thermoforming, and hot melt extrusion. So hot melt extrusion is very commonly used in the packaging industry to apply a thin film on top of the paperboard. So the main advantage is that they provide barrier against water vapor. So if you look at different kinds of thermoplastics available, we can sort them out into different groups depending on their source, if they are fossil fuel based or if they are bio based, and then also depending on their end of life, if they are non-biodegradable or biodegradable. So if you go to the top right, they are the most ideal ones. So where they are both biodegradable and also bio-based. So PLA and PBS, for example, fall in that category. And then we have the conventional ones like LDPE and other polymers. And then there are these fossil fuel based but still biodegradable, such as PBATs and PCLs. So here we chose three different polymers. So one is LDPE as a reference, and then there is a commercial product Ecovio from BASF, which is a blend of PLA and PBAT, and then PBS, which is both biodegradable and bio-based. So when we coat the nanocellulose paper, we took that to Tampere University. They have a pilot scale extrusion coater. So, and then we coated these three materials on top of nanocellulose, and then we looked at how the barrier properties change. Here are some cross sections. So from the top, we have with LDPE. So we have the baseboard here, pigment coating, the white one, then MFC layer, and then an LDPE layer on top. And then the second one is with the Ecovio, slightly bigger, thicker layer. And then on the bottom, we have PBS. So now there are different chemistries between that work with that help with the adhesion. So a PBS, for example, doesn't really adhere very well to nanocellulose. So here we can see in the cross-section image that there is a very thin gap in between both the layers, and then we could actually peel the top layer off with just the hand. So one workaround is that we can blend pigments into nanocellulose, and then that will create a bit rougher surface, changes the surface chemistry, and could help with the adhesion. So on the right image here, we added 40% KLN. This is hyperplatic KLN with a very high aspect ratio. and then the adhesion issue kind of gets solved because the surface gets a bit rougher and the chemistry is changed. Other alternatives could be that plasma treatment before extrusion coating, or instead of blending pigments, we can have a very thin layer of pigment coating on nanocellulose and then have the extrusion coating on top as well. So here are some results from barrier measurement. So most important one with the whole multi-layer concept is to see how water vapor barrier is influenced. So these are all for roll-to-roll coated paper. So we did it at two conditions. One is at 23 degrees Celsius and 50% humidity. And then the other is a much more tropical condition, 38 degrees Celsius and 90% humidity. So we see both nanocellulose, MFC and CNF, they do not have a very good barrier. So their values are very high. And then the moment we coat the extrusion polymers on top with LDPE, we get over 95% reduction. And then with the other biodegradable polymers, we have over 72% reduction, which is an improvement. And then oxygen barrier. This is one of my one of the interesting results we found. So these results are these measurements are done at 23 degrees Celsius and 50% humidity. So I want to start with the small image on the top right. So here we compare the oxygen permeance values between Petri dish films that was made in a batch process and under very controlled conditions, and then the red bars are the roll-to-roll coated ones. So when we do it in a batch process on a Petri dish, we get very good oxygen barrier. Like these are very small coatings. These are adjusted for the same thickness. So this is about 5 to 8 micrometer films. So MFC and CNF, they have like pure films, both have very good oxygen barrier. But the moment we do roll-to-roll coating, the barrier gets really, really bad. And then the error bars, they look small, but if you look at the scale, it's on a logarithmic scale. So there's a very big variation as well. So one reason we don't get oxygen barrier when we do roll-to-roll coating is that the drying conditions are quite extreme. The temperatures are close to 200 degrees Celsius. So that will lead to cracks in the coating layer when in the nanocellulose coated layer. And then once we have cracks, then the oxygen passes through, and then we don't have a barrier at all. But then an interesting thing happens when we do the extrusion coating on top. So on the bottom, I have the values from the roll-to-roll coated multi-layer samples. So the red ones are the reference for pure polymer, and then the blue and green are when we have a multi-layer structure with nanocellulose in them. And here we see that the barrier improves and then almost is the same as what we get for the pure films. So one probable reason is that when we do the extrusion coating, we have a nip and then we have a high temperature molten polymer. So that would both plug the pinholes and then also kind of plasticizes the nanocellulose layer and kind of helps fill in any cracks and defects. So that is a very positive effect. So multi-layer coating not just improves the water vapor barrier, but also helps improve overall barrier as well. And yeah. And here it's the same oxygen barrier, but influence of pigment additives and glycerol. So these are also measured at 50% humidity and 23 degrees Celsius. And all measurements are for the roll-to-roll multi-layer coated paperboard. So on the left side is the influence of kaolin. So like I said before, when we add pigments to the nanocellulose, it helps with adhesion to the polymer on top. So that is why we wanted to see how much pigment could be added and how it would influence the barrier performance. So these are for three different polymers when we have LDPE, Ecovio, and PBS, and this is for MFC. So at 0%, so this is the initial barrier which we have, but then as we increase the pigment blend, then the barrier starts to go bad. But up until 10%, we see that the barrier doesn't is quite okay. So a small percentage of pigment is useful in this sense that it improves the adhesion and still keeps the barrier intact. And then on the right side, we have influence of plasticizer, like we added glycerol to CNF. Here we, again, the same three different polymers, and then we start with 0%, which is the just pure nanocellulose. And then as we add glycerol 2 and 10%, we see that the barrier kind of gets a bit better and then flattens out. So the reason is that, again, when we have glycerol, it makes the coating layer a bit flexible. So it kind of like prevents the cracks and pinholes that form when we do the roll-to-roll coating. So that is an added advantage. And also when we want to use it as a barrier packaging, then the board would be creased to different shapes. So the coating should be a bit flexible. So in that sense, having a very small percentage, like here even at 2% glycerol addition, helps with the barrier quite a lot. And then we have the influence of relative humidity. So this is for MFC coated with LDPE on top. And then we have one coating where we have a LDPE coated on the bottom side of the paperboard as well. And we did it at 3 different conditions with increasing temperature and humidity. So we go from 23 degrees Celsius to 38 degrees Celsius. And then the humidity also goes from 50 to 90%. And as the humidity goes up, the oxygen barrier gets worse. So even we have LDPE on the bottom side, it is kind of better, but still not that great. So the reason is that at higher humidities, as nanocellulose absorbs moisture, it starts to swell, its network starts to break down or gets disturbed, and then it loses its dense packing, which provides oxygen barrier in the first place. So this is one issue, and even having LDPE on the bottom side didn't help much because there is still water vapor that absorbs through the sides along the cross section. So one workaround could be to just sandwich nanocellulose in between water impermeable layers, like have a water barrier coating and then nanocellulose and then water barrier coating on top. So that is something that we are now trying to do. But yes, this is one of the issues with oxygen barrier at higher humidities. Then we have grease barrier. So the way we do this test is we have the paper and then we place some olive oil on top and weights on the 50 gram weight on the top side, and then everything is kept in an oven at 50 degrees Celsius, and then we see how much time it takes for the olive oil to pass through. And this process is kind of automated because we have a scanner at the bottom which scans at regular intervals, and then we have an image analysis software that plots the area of the oil that is penetrated as a function of time. So here we took about 1% area. If it is covered with oil, then the barrier is gone. So if you take that, here I have values for pure MFC coating, very high variance, and then also the barrier gets bad as we increase kaolin. Same with CNF, we have very high variation. Again, the same reason is that there are cracks and pinholes, and then oil finds places to go through. But then when we have a multi-layer structure, then it has the same effect as the oxygen barrier. It seals them up, and then we don't have any failure at all. Yeah, and then also this test was run for over about a month, about 500 hours, and we still do not see any failure there at all. Then we have a mineral oil barrier. So mineral oil barrier is important if you want to have some kind of printing on top of the paper. And then most of the printing processes, they have some kind of mineral oils in them. So there needs to be barrier against that. So one way to test is to see for heptane vapor transmission rate. So we have heptane in a cup and then seal close the top with the paperboard and then see how much vapor escapes over time. So this is also done at 50% humidity and 23 degrees Celsius. So nanocellulose have very good mineral oil barrier. So when we have MFC and CNF coatings, the heptane vapor didn't escape at all. So I didn't put them here. And also EcoVio and PBS, this PLS, PBAT, and PBS, all of them have a very good mineral oil barrier as well. So I didn't use them here. And LDPE doesn't have mineral oil barrier. So like it has about 640 grams per meter square per day of vapor escaping compared to MFCs and CNS, which is almost zero. So here I have how kaolin influences. So it's the same story. If you have more kaolin, then the barrier gets bad, but up to 10%, it is quite okay to do this. And there is another test called KIT test, which is also a very similar test. So it goes from 1 to 12, being 1 being low barrier and 12 being higher barrier. And for all the samples, we get a value of 12 or higher. Yes. So in summary, we used 2 continuous coating methods in tandem to produce multi-layer barrier paperboard. So first one is a slot die coating of nanocellulose. And then we complement that with an extrusion coating of thermoplastics on top for moisture barrier. And in addition to moisture barrier, extrusion coating helps to offset any coating defects and improves the overall barrier. And when we have pigments into the blended into nanocellulose, it helps with adhesion with thermoplastics, and plasticizers will help also with more uniform coating, and then which leads to a better barrier. If we sandwich nanocellulose between water impermeable layers, then we could have much better oxygen barrier at higher humidities. And I want to end by coming back to this original figure from the initial slides. So the green ones are the samples that I have talked in this work. So when we have LDPE on top, and then we have nanocellulose, so they actually fall into the red box. They're almost as good as metallized plastics. So we can, for example, get rid of aluminum here. But still, they have LDPE, which is not biodegradable. But if you look at the other ones in the red circle there, all of them, both the oxygen and water vapor barrier has improved, and these ones are 100% biodegradable. Yeah, thank you.
Thank you, Rajesh. So we are ready for a couple of questions. So while you prepare your questions, just for those of you who have to leave now, because we're at the mark of the 2:30, so I welcome you back on the February EPNOE webinar. So we are going to take a rest in January and then continue in February on the theme of chemistry. However, now we are ready for questions.
Yeah, I may start.
Go ahead, Pedro.
Rajesh, thank you very much. Very nice presentation of Akademi. Does very nice work on this coating research that is very special, very specific. I have a question. I mean, we are talking all the time, and you also mentioned about circularity. Yeah? I mean, and you are comparing barriers, like you are using polyethylene, low density polyethylene, for example. Do you think that cellulose can you produce barriers that are going to be recyclable or biodegradable? What will be the main advantage of using the nanocellulose here?
Yes, so the only reason we have low density polyethylene here is to show as a reference. But we did use these other biodegradable plastics such as PLA and PHAs, and then there are also other I would say cellulose based things, like we have this barriers based on dispersions based on hemicellulose, modified hemicellulose. So nanocellulose here is good in the sense that it has very good oxygen barrier and grease and mineral oil barriers. So it just needs some support on the top to have some moisture barrier. So as long as we have some other coating which is also biodegradable that can give moisture barrier, I think it is these are quite good at getting being much more circular.
And do you see this as the technology can be competitive to using the low cost synthetic ones?
Right now it is not very competitive. It is a bit expensive, mainly like one nanocellulose is still very expensive to get, and then also they have these higher energy costs to dry the nanocellulose especially. But I see a lot of research happening, like for example in this work we did 2% or 3% nanocellulose, but now there are already these enzymatically pre-treated nanocelluloses which are available at 20% and even 30%. Well, to coat them with good quality or not, I think some research needs to be done, but I see a trend towards that as well, like more higher solids one, which is more industrially relevant. And then also there are more now pilot scale nanocellulose producers in the all the big major paper companies are trying to produce it. So yeah, I think the industry is trying to go there, and there is this all the regulations which are also pushing the trend towards that.
Do you think what is the bigger challenge, the cost of nanocellulose as a material, or the drying challenge and cost?
I think both are equally big challenges. Because producing nanocellulose is still expensive, and also energy is also one of the bigger challenges. But then if there is an integrated paper mill, for example, they are mostly energy positive, so they can kind of work with a bit more energy. And then also they are mostly nanocellulose producers as well, so there is less cost involved in transportation and logistics.
Do you think that incorporating nanocellulose into this multi-layer packaging materials would drastically change this picture that you had in your first slide? A little bit what Pedro was referring to, this challenge of circularity and recycling. So how will that picture change in the long run?
Yes, I think it will change in the long run, because these materials that we have been working on, like nanocellulose and all of these, they are biodegradable. Well, recyclability is still being looked into, but at least they are biodegradable. So even if they are not recycled, still they will not cause problems.
Yeah, of course, the recycling is a field of its own, right? So it has its own challenges. Great. Okay, so then I think we finished there. Thank you, all our speakers. Thank you for the audience for joining. We will continue with these webinars. It is a monthly webinar. We will skip January so we can all get the rest. And then we will keep going in February, where we will talk about chemistry of polysaccharides. So thank you for joining today, and welcome to join again in February.